Good morning, sir. Good morning, fellow students. Welcome to System Dynamics and Control class 4312, section 063. For my final project, I'll be talking about heat exchangers, specifically the shell and tube heat exchangers. So, as I mentioned earlier, for the abstract for this project, I spoke about a heat exchanger, what a heat exchanger is. A heat exchanger is a device used for transferring heat from one medium to another. It could transfer heat between two or more fluids. There are a few types of heat exchangers. We have a shell and tube, which I'll be talking about. We have a heat exchanger, plate fin heat exchanger, and some other rest. So this is the design that I'll be talking about. This is shell and tube. See the shell is this box right here, and then the tubes are going in horizontally through the shell, separated by some baffles. Uh, so what's the purpose for this project? So this project is to determine ways to have sufficient oxygen in mass, and we have to design a shell and tube heat exchanger. Also calculate the overall heat exchange, and also the pressure drop on both sides of the shell and the tube side. Okay, the need for this project, as I mentioned, is to have a way to produce sufficient energy or oxygen in mass. Um, Also, because of the high energy required to produce oxygen, shell and tube heat exchanger will help us maximize that energy. So, the methodology for this experiment. This is the setup will be to design an experimental setup to collect data from a heat exchanger. The objective will be to develop an efficient heat exchanger that help bring temperature close or high enough to reduce the energy needed for the SOEC. So improving the effectiveness of the heat exchanger will be a priority in this my experiment, and the setup will be as follows. This apparatus, as you can see. These are the shell, these are the tubes, and then the shell from this apparatus that I designed. And the results. So what happened is I assume, because I had to assume our temperature going into the shell, which is 25. I assume it to be room temperature. That would be the cooling temperature, the T code, and assume a high temperature of 99.2, which I had to look it up for. I had to look it up, and then, but through my calculations, I had a T code that came out to be T code from the shell side that came out to be 54.3, and the T had 37.6. So these are the assumed dimension I used for my diameter, outer diameter, inner diameter, the number of tubes, as you can see in the picture, 6 tubes, and then the length of 6 feet, and then this the diameter, effective diameter for the shell. All these values were to go in with the calculation, and in my project, in my Word document, I couldn't fit everything here in this PowerPoint. You see the calculations, and you see how I did to get these Qs, which are the heat duties, and this is the heat duty of the shell side. You see the heat duties of both sides are equal, and then this is the heat duty of the overall heat exchanger, 88.5 watts. and then you see the NTU and the Cmin 0.06 kilowatts, which is approximately 1.6 watts. And this is the formula used to calculate the Q, the overall Q. For the discussion, so in my project, from my project at the main project at the Wards 5, most of the discussion is on there, so I'll just say why I came up with this discussion. So from the experiment, we'll notice that some heat was transferred from the hot flow in the tube to the air that flowed through the shell, but much heat was lost to the surroundings as the hot temperature through the tube reduced significantly. Like you can see from the calculations, how it reduced from 99.2 to 37. So it means, and then the heat gained by the cold fluid was just 50 something. So you see, much heat was lost to the surroundings. This could be because of the fouling factor, which I didn't consider in this experiment, and the heat loss to a number of baffles in the shell. Also, as heat transferred to the shell surroundings. In this experiment, I assume I placed some coatings on the shell to reduce heat loss. So to increase the overall heat transfer, some few things are noted from the calculation that could help increase overall heat transfer. Was the mass flow rate needed to be increased, as well as the number of baffles. This number of baffles increases the number of passage, that reduces the time it takes for the fluid to flow through a tube. To flow through a passage, it reduces the time it takes for the tube, for the cool air to flow through the passage in the shell. So this also increases the heat transfer, and also increasing the velocity or reducing the velocity will increase the heat transfer. Also, the number of baffles increase the area, like what I said, when the area of the shell increases, so there's more surface area for the heat exchange to take place. So these factors could increase the pressure drop as well as velocity increases. So those are the things I noted during the calculation that could help increase the overall heat transfer. So conclusion. So this project, the result from this project gave the opportunity to propose solutions to improve the heat transfer and to explore potential modification on different parameters to maximize heat transfer and reduce the required operating power. Because the operating power right now for the production of oxygen is really high, so if this one could increase heat transfer and then reduce that energy, it is going to be a good project. In this experiment, those factors include but are not limited to correction factors, surface area, temperature difference, etc. Knowing the importance of the use of heat transfer, designing a maximum efficiency is vital. So based on the result, the values of pressure drop were low. There was also a significant difference in temperature difference. The desire was to get a higher temperature as a result of the inlet 25 to produce a 54. We needed a higher temperature, so maybe some of this modification, limiting correction factor, surface area, increasing surface area, could increase this outlet temperature to probably 60 or 70, which is what will make a really good heat exchanger. So from the understanding of the project, I understood that most heat was lost during the transfer. So thank you, class, and thank you for listening to me.